Okay, so this is going to be our last section of Chapter 4. So our last Chapter 4 video, and we're going to deal with projectile motion. Okay, so let's get this slideshow set up. All right, so projectile motion. So just think about if you are, if you're walking and you have a ball and you're dropping the ball and bouncing the ball, and you're walking, or in this case, this kid is roller skating, looks like. So you're moving horizontally, but that ball is going up and down as well. So we have two types of motion. We have a horizontal motion and we have a vertical motion, and they are acting independently of each other. So the ball continues to go forward, even though it's also going vertically. So it's going to continue to go horizontally as you move horizontally, but it's also going up and down because you're bouncing it up and down. Okay. So let's move this up. So we have to take into account both of those types of motion. So let's look at the definition of a projectile. A projectile is an object that is launched and then allowed to follow the path determined solely by gravity. So you drop it and then you don't touch it anymore. You don't do anything into it anymore. It doesn't have a motor on it. It doesn't have anything. The only thing that is determining its motion after you launch it and let go of it, the only thing determining its motion is gravity. So regardless of how the projectile is launched, its path is always a parabola if we ignore air resistance and the acceleration due to gravity is constant and, of course, directed downward because we know gravity is always pulling things downward. Okay. So that path, that parabolic path, is produced by a combination of the horizontal movement forward and the movement down. And both of those acting independently causes that shape of a parabola. So it's going up, or in some cases, it's coming down, or it's going up and down, but it's also moving forward, and that gives us that shape of that parabola. So we can use the same position versus time equations that we used in chapter 3, but we're going to apply them to both the x motion or the horizontal motion, and we're going to apply it to the vertical motion up and down. So we use a coordinate system when we talk about the motion of a projectile. The positive y position is going up and the positive x position would be going to the right. So this is our coordinate plane. So positive y goes up, positive x goes to the right. And so you notice that if your acceleration is going down, then that's going to be a negative number. Okay. The acceleration due to gravity is always going to be a negative number because gravity is pulling it down, and that's the way it's acting. So that's going to be a negative 9.8 because that shows the direction in which it's moving. All right, so here are the equations that we had in chapter 3 that we've kind of adjusted now for parabolas. Remember, since we have two motions, we have an x motion and a y motion, we have to include two equations. Okay, so this is our equation for the final position in the x direction, and this is the final position in the y direction. Okay. So you'll have the initial positions would be xi and yi. The initial velocities would be the initial velocity in the x direction and the initial velocity in the y direction. Okay, now there is no acceleration in the x direction, so that ax is always going to be 0, and the acceleration in the y direction is always going to be equal to gravity. That's going to be negative 9.8 meters per second squared. So let's look at a sample problem to get an idea of what we need to do with this. So this is on page 133 of your textbook. So the figure that they're talking about is on page 133, And it's basically just a guy who is skateboarding and bouncing a ball at the same time. So, a person skateboarding with constant speed of 1.3 meters per second releases a ball from a height of 1.25 meters above the ground, in figure 425. Given that the initial x position is 0, the initial y position is 1.25 because that's where he drops it from. So he's skating along and he's going to drop that basketball. And he's holding it 1.25 meters above the ground. So that's your initial y position. Your initial x position, where he started, that of course is going to be 0. For xf and yf, find the times at equals 0. Find x. I said it backwards. Find xf and yf where the times t equals 2.5 and t equals 0.5. Remember that g is 9.8. So we're just going to go back to our original equations. So let's write those original equations up here. So we have xf equals xi plus vxi t. And this is yf equals yi plus vyit plus, nope, not a plus, sorry, minus 1/2 gt squared. And that minus sign in there accounts for our, hang on. So then we're just going to plug our numbers in. So we're going to put in xi as 0, so that whole thing is going to fall to 0. Then we're going to put in our time and our speed right here. So that's what this equation will turn into. And then we're going to plug in our initial position for y is 1.25. And the vyi, the initial velocity in the y direction, there is no initial velocity in the y direction. Okay, so that would be 0. Okay, so because horizontally he's on the skateboard and he's moving at a speed of 1.3 meters per second, but he's just holding the basketball. The basketball's not moving till he drops it, and even then it's starting at a velocity of 0. So that whole term goes out to 0, and you get 1.25 minus 1/2 gt squared. And so then we're just going to plug those numbers in. So we're going to plug in 0.25 and a g of 9.8 meters per second squared. So 0.250 times 1.3 gives us our 3.25. And then we have 0.5 times 9.8 times 0.25 squared. And then we're going to subtract that from 1.25. Okay, so this negative already takes into account the fact that our gravity is acting downward. So in here, we put in 9.8. We don't put in negative 9.8 because we've already accounted for that in our equation to begin with. So you would have 1.25 minus 1/2 times 9.8 times 0.25 squared. Okay, then you'll just do the same thing again for B. Okay, so that's important for you to remember. The equation already takes into account the negative value of the gravity, the fact the gravity is acting downward. So you don't need to put it in twice. You don't need to put in negative 9.8 for G, you just put in 9.8. Okay. All right, so here is another example. You throw a ball from a roof of a house to a friend on the ground. The ball has an initial velocity of 12 meters per second in the horizontal direction. So when you rear it back and you've thrown it at a speed or a velocity of 12 meters per second in the horizontal. So that's your Vx. After 1 second, how fast is the ball moving? A, in the x direction, and B, in the y direction. Okay, so the velocity of x doesn't change. So its final velocity in the x direction is exactly the same as what it started with, because the only thing acting on that ball is gravity, and gravity is acting down. Okay, so its velocity in the x direction is going to stay constant. For the y direction, you're going to put in your time of 1 second into your VYF formula. So your VYF is equal to your initial velocity in the y direction minus GT, which our initial velocity in the y direction is 0. So we're going to put in minus 9.8 meters per second times 1 second. So its final velocity in the y direction would be negative 9.8 meters per second. Okay, here's another example. Let's make sure that I have, yeah, okay. Another example, same thing. You have people diving off of an overhang. Diver 1 drops straight down. Diver 2 takes a running leap. Okay, so it has an initial horizontal velocity, and the splashdown speed of diver 2 is it greater than, less than, or equal to that of diver 1. Diver 2 falls for the same amount of time as they both fall for the same amount of time because the only thing bringing both of them down is gravity. Diver 2 also has an x component of velocity, so the speed of diver 2 is going to be greater. So when he hits the water, he'll be going faster because he has an x component and a y component, whereas diver 1 only has a y component to deal with. So diver 2 will have a greater speed when he hits the water than diver 1. So projectiles can be launched at any angle, doesn't matter. They're all going to do the same thing. They're all going to form that parabola. The shape of the parabola may be different depending on the angle, but that's all. So this equation looks at how to determine the speed, the initial speed in the x direction and the initial speed in the y direction when you launch it at an angle. So we're not just dropping it straight down anymore. We're launching it, or it's moving at some angle. And that just goes back to what we learned previously in the chapter, where we take this velocity vector vi and we break it up into its components, vxi and vyi, and we use our trig functions to find the initial velocity in the x direction and the initial velocity in the y direction. That's going to be equal to, the cosine of theta would be adjacent over hypotenuse, so we're solving for xi. So that's going to be equal to our hypotenuse times the cosine of theta. If we're looking for xy, that's going to be the resultant times the sine of theta. All right. So here are those equations for when a projectile is launched at an angle. So again, we're not just dropping straight, we're launching it. So xf, the final position in the x direction, is the initial position in the x direction times the initial velocity times the cosine of theta times the time. And the initial y position, final y position, is equal to the initial y position plus the initial velocity times the sine of theta times time minus 1/2 gt squared. And then here are the equations for velocity versus time. Okay, so you will have these equations on your test. You'll have them listed there, but the main thing you're going to have to do is know how to pick which one and in what circumstance. Okay, so I think we'll come back to this equation later, or that problem later. Let's talk about the range. The range of a projectile is the horizontal distance it travels before it lands. So, and this is the equation for determining that. The range is equal to the initial velocity squared, so how fast it's going horizontally initially, divided by gravity, or the initial, not horizontally, the initial velocity squared divided by gravity times the sine of 2 theta. Um, okay, and we know that most everyday objects can act as projectiles, especially if we don't incorporate air resistance. And we found that for objects launched, the best angle to cover the most ground to give the largest range will be an angle of 45 degrees. Air resistance, if we incorporate air resistance, if we have a lot of air resistance and we can incorporate it, then all that does is it reduces the range and alters the shape of the trajectory. So instead of being nice and wide, it's kind of skinny. Um, that's the only difference between incorporating air resistance and not incorporating it. It'll change the shape of the trajectory, the path. Okay. All right. So let's go back to that equation or that practice problem here. All right. Let's try and move that up a little more. So this is 412 in your book. So chipping from the rough, a golfer sends the ball over a 3-mile high tree that is 14 meters away. The ball lands on the green and, of course, the same level at which it was struck after traveling a horizontal distance of 17.8 meters. If the ball left the club at an angle of 54 degrees above the horizontal and landed on the green 2.24 seconds later, what is the initial speed? And then the ball passes directly over a tree at t equals 1.76 seconds. How high was the ball at that time? So we've drawn our little sketch, and like I said, with these types of problems, these vector problems and trajectory problems, you really need to draw it out. So here's our distance in the x direction. Our height is going to be our y direction. We're at an angle of 54 degrees, so the ball is going to go up, 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 and then come back down. We're told that it comes down 17.8 meters away. So that's where it lands. We're told that we have 54 degrees, and we're told that our time is 2.4 seconds later. So this whole distance here is covered in 2.24 seconds. And then it passes the tree, which is right here, in 1.76 seconds. All right. So our initial x direction and our initial x position and initial y position are both 0 since you're starting on the ground. XF is 1.78 meters, and our final y position is going to be 0 because, again, it lands on the ground. And so we're going to use those other factors as we plug into our equation. We can find the initial speed, because remember, that's what we're trying to find. If the ball left the club, what is the initial speed? So we can plug into that equation for XF equals XI plus VI cosine theta t. And I'm going to use that one because I know all the variables except the one I'm looking for, which is, VI. That's the one I'm looking for. So I know my XI is 0. I know my XF is 17.8. My angle is 54. And my time, I know, is 2.24 seconds. Okay? So I'm just going to plug in and find VI. To do A. To do B, we're going to use 1.76 seconds. And we're looking for how high it is. So we're looking for a Y position. Okay, so I'm going to use the equation for YF. Okay, my initial Y equation is 0. My VI I found in A, and my G and my T are constants, and I'm given those. So I can easily plug into there and find the final y position, which would be where this is at that particular time. Okay, so then they plugged all that in. You can see them doing the algebra there. Now, I like to rearrange my equation first before I put the numbers in. It just helps me make sure that I've canceled everything out correctly, which is sort of what they did here. They plugged in the 0 for xi, and then they just solved this for vi first, and then put the numbers in. To me, it just makes it easier to find your mistakes. And then we're going to do the same for YF, except in this case, we are looking for YF, and it's already solved for YF, so we're just going to plug the numbers in and work it out. Okay. You throw a ball to a friend with an initial speed of 10 meters per second. Your friend catches the ball at time capital T at the same level from which you threw it. Referring to the figure below, which of the plots, 1, 2, or 3, best represents the speed of the ball as a function of time? So the ball is thrown in a direction above the horizontal, so its speed is going to slow down. So you're throwing it up, and so it's not going to gain speed. It's going to slow down because gravity is beginning to pull it down. So since it's not gaining speed, it can't be right there. Of the two remaining plots, we can estimate that speed. We can eliminate 3 because it goes below 0. Well, you can't have a negative speed. Okay, so you can't go below 0. Because it shows the speed going to 0 at halfway through the flight. It can't go to 0 halfway through the flight. Because if it does, it's stopped. It has no more flight. So that can't be it. So it has to be 2. And we talked about those other things before. Okie dokie. All right, so that is it for projectiles.